If you're the kind of person who really wants to understand the actual nuts and bolts of massive energy systems, you are in exactly the right place. Today, we're going deep inside the design phase. We'll be looking specifically at Chapter 3 from the source material, taking a fully chronological engineering deep dive into what's known as Project 3. We are going to break down the entire design of a 1.1 megawatt peak solar PV plant, totally integrated with 7 battery energy storage system units, all operating completely off-grid in an isolated island mode. I'm incredibly excited about this one, because we are looking at everything: the design steps, the calculations, the final drawings delivered, the whole shebang.
Okay, let's dive right into this. Here is our roadmap from concept to blueprint. First, an overview of Project 3. Then, BESS sizing calculations, system architecture and equipment, civil works and site layout, and finally, those crucial final engineering deliverables.
1.1 megawatts peak. Just let that number sink in for a second. That is the headline capacity of this commercial and industrial scale off-grid system. I want you to keep this massive number in the back of your mind, because it really sets the stage for the sheer scale of the math, the equipment, and the intense engineering rigor we're about to explore. When you're dealing with over a megawatt of direct current power that is completely disconnected from a utility grid, every single calculation has to be absolutely flawless.
So, let's start with Section 1, Overview of Project 3.
Here we have the actual project setup, straight from the Eco-Egypt Utility Scale PV Training Program. What we're looking at is a commercial and industrial facility operating entirely in island mode. And if you're familiar with the term, you know that means there is zero utility grid connection to fall back on. No safety net. The facility survives by perfectly balancing a solar PV array, a battery energy storage system, and a diesel generator. Literally, if the design fails, the lights go out. Let's put some hard numbers to this so we can anchor these theoretical concepts into the physical world. Our PV DC capacity is that 1.1 megawatts peak. That's paired with a BESS nameplate capacity of 1,505 kilowatt hours, which is actually made up of 7 individual 215 kilowatt hour units. The facility itself has a peak demand of 500 kilowatts, and to handle all that solar conversion, the design uses 7 Huawei 150 kVA inverters. Notice the perfect symmetry there? 7 solar inverters and 7 BESS units. We are definitely going to see why they made that architectural choice in just a minute.
Moving right along to Section 2, BESS sizing and calculations.
Sizing a massive battery system? Absolutely not a guessing game. It follows a very strict engineering methodology. These are the 5 mandatory steps every engineer has to take. Step 1, figure out your plant demand and import limits. Step 2, calculate the actual BESS power you need. Step 3, pinpoint how many hours of peak duration you're designing for. Step 4 gives you the raw energy required. But Step 5 is where reality hits. You have to apply your battery losses, factoring in things like depth of discharge and efficiency, just to find out the physical size of the battery you need to buy.
Let's actually zoom in on those Step 5 losses for a second. So our BESS nameplate rating is 1,505 kilowatt hours, right? But you can't just use all of that. To protect the lithium iron phosphate cells, those LFP cells, and make sure they actually survive for their 6,000 cycle lifespan, the system imposes an 80% depth of discharge limit. As this chart breaks down, that means you only get 1,204 kilowatt hours of actual usable energy. That remaining 301 kilowatt hours, it's held back purely to prevent degrading the batteries. And this brilliantly illustrates how we arrive at one of our most critical operational metrics, autonomy. If we take that usable energy, the 1,204 kilowatt hours, and divide it by our facility's peak demand of 500 kilowatts, we get exactly 2.4 hours. Practically speaking, this means if a massive storm rolls in and blocks the sun during a peak load event, the facility can run purely on battery power for roughly 2.5 hours without even thinking about touching that diesel generator.
All right, let's jump to Section 3, Core Equipment and Architecture.
When you're completely cut off from the grid, your energy management system, the EMS, is basically the brain of the whole operation. And it follows this incredibly strict power priority sequence. The absolute top priority is using the PV generation. That free solar energy goes straight to the facility's load supply. If there's any left over, it charges the BESS. Only as an absolute last resort does the EMS fire up the diesel generator. This logic is called fuel saver mode, and the entire point is just to ruthlessly minimize expensive diesel fuel consumption while maximizing that free solar power.
Now, what's really interesting here is the sheer level of engineering detail needed just to keep things safe. This is the AC single-line diagram for the outdoor main distribution board. If you look closely at those circuit breakers, you're going to see they're marked as 4P or 4-pole. In an isolated off-grid system, 4-pole motorized neutral switching is absolutely non-negotiable. You can't just switch the 3 phases, you literally have to switch the neutral line too, just to safely isolate the PV, the batteries, and the generator from one another.
Remember earlier when I pointed out that symmetry? Well, here is exactly why that matters. The architecture perfectly pairs 7 of those Huawei 150 kVr solar inverters, each handling 14 strings of panels, with 7 of the 215 kWh LFP battery containers. What makes these specific battery units such a game changer is that they have built-in bidirectional power conversion systems, or PCS. Because it's a one-to-one match, these units can handle simultaneous charging and discharging across the whole site without creating any awkward power bottlenecks.
Which brings us to Section 4, Civil Works and Site Layout.
Okay, so what we're looking at now is the actual blueprint. This is where the theoretical math hits the dirt. It shows precisely where all 1,764 solar modules are going to sit. Look at the spacing between the rows. That's not random. It's mathematically calculated to ensure shadow-free operation even during the winter solstice when the sun is super low in the sky. And down at the bottom, you can see the dedicated foundation pads for those 7 BESS containers, all tied together by an underground trench network.
Because look, before a single piece of fancy electronics even shows up on site, the civil engineering has to be absolutely spot on. As you can see, those 7 BESS foundation pads require heavy-duty reinforced concrete with embedded anchor bolts and cable ducts. The inverter pads need special anti-vibration mounts. And check out the trench specs. The DC cable trenches have to be dug exactly 1 meter deep and 1 meter wide, laid with a 100mm sand bed. The earthing trench goes down a full 2 meters. It's these physical concrete details that guarantee the plant will actually survive and operate safely for decades. And finally, Section 5, Final Engineering Deliverables.
Let's move on and see how all of this builds into the Final Engineering Deliverable List, or the EDL. Honestly, this table is like the engineer's final exam. It's the ultimate proof of work for the entire design phase, showing the client that every single component, every wire, and every logic sequence has been calculated, simulated, and officially documented.
Just to give you a sense of the sheer volume of work here, the base design package is massive, and it has to be cleanly categorized. We're talking about everything from the design steps and mathematical calculations for battery, cable, and earthing sizing to the final physical drawings delivered. You've got software simulations like PVsyst and Homer proving the math holds up over an entire year. You've got hundreds of pages of datasheets and the final bill of quantities. And remember, all of this happens before a single wire is ever touched on site.
So the really crucial takeaway here is summed up perfectly in this quote from the design basis. The success of this entire 1.1 megawatt peak project relies 100% on the precision of that automated control logic we just went through. Because the system is completely isolated from the grid, there is zero room for error. The EMS has to act as an invisible, flawless operator, perfectly balancing the sun, the batteries, and the diesel generator 24/7.